Okay, quickly, I already gave you the extension on this assignment. So this assignment is extended by the end of this week. So make sure that you verify your code, verify your answers with the actual robot. Take the snapshot of the virtual robot or take the snapshot of the actual robot and add that as evidence that your forward and inverse kinematics is giving you the right answer. Now, in today's class, I want to work out two problems. These two problems are very important because remember, we talked about the rules. We talked about the forward and inverse kinematics rules. So forward and inverse kinematics rules. So rule number one is Z passes through axis. Then second, you have xn intersects is perpendicular to Zn, intersects Zn minus 1. And the third one is you have the right hand coordinate. Now let's try to work out an example where these rules are violated. So let's start with a robot. You have the first revolute joint. Then you have this second revolute joint. And then at the end of the second revolute joint, what you have is you have this prismatic joint. So at the end of the second revolute joint, you have this prismatic joint. So first and foremost, this robot is R, perpendicular R, and then what you see is you have the last, which is perpendicular P. So what you have is you have R, perpendicular P. First revolute joint, second revolute joint, and prismatic joint. This guy, last point, is the end effector. Need to set up the coordinates. So first, this is Z0, this is Z1, and note, the third joint is not a revolute joint, it's a prismatic joint. So my Z2 needs to pass to the prismatic joint. So this is going to be my Z2. This is going to be my Z2. And then I'm going to assume this to be my Z3. Everyone okay with Z1, Z2, Z0, Z1, Z2, and Z3? Now I need to specify X0, X1, X2, and X3. Now please pay attention because this is where the things are going to get tricky. So I'm going to assume this as X0. Okay. Now what I need to do is I need to find out what is going to be my X1. So this is going to be my X1. Do you agree with me? Because this X1 is perpendicular to Z1 and perpendicular to Z0. It intersects. No problem here. Now my question to you is, when I want to draw X2, where should I draw it? So I give you choices. So X2 can be here, X2 can be here. So tell me, where should I draw X2? You agree with me? Okay, let's look at the possibilities. If my X2 is over here, let's assume this is my X2. This is my X2. Do you agree with me that this X2 is perpendicular to Z2 but does not intersect Z1. Once again, this Z2 and X2, they are perpendicular to each other. But this X2 does not intersect Z1. You agree with me? There is this huge gap, this offset. Some of you may say, why not to draw X2 here or here? Even if I draw X2 here, or even if I draw X2 here, you agree with me that there is this constant offset that you cannot ignore. You agree with me? Which means no matter where you use your X2, where you draw your X2, X2 is not going to intersect Z1. You agree with me? Which means rule number 2 will never get satisfied. In that case, what? In that case, we continue as is. We continue as is. We know that frame 2 does not follow rule 2. So frame 2 does not follow rule 2. Let's go to the next frame, Z3, and I'm going to assume X3 over here. Why am I assuming X3 like this? Because if my X3 is aligned with my X2, my Z3 is aligned with my Z2, clearly my Y2 will be aligned with my Y3 and my projection matrix would be identical. Now I would complete the triad. Curl your fingers, X, Z, Y. Why not? You have X, Z, Y. Then you have X, Z, Y. So you have X, Z, Y comes in this direction. Y2 and this comes as Y3. You agree with me? Now my right hand coordinate system is set up. Now what I need to do is I need to find the rotation matrices, I need to find the projection matrices, and then I need to set up the homogeneous transformations. So I'm gonna give you some values here. This is going to be my A1. This is going to be my A2. And this guy is going to be my A3. A1, A2, A3. So start with 0R1. So I'm going to say this one is theta 1. This one is theta 2. And please understand, I don't have a revolute joint. I have a prismatic joint. Prismatic joint does not have any rotation. It has displacement. So I would say this is my D3. So D3 is the extension of the prismatic joint. So let's start 0R1. 0R1 cosine theta 1 minus sine theta 1, 0, sine theta 1, cosine theta 1, 0, 0, 0, 1. What am I missing here? Multiply this by a projection matrix. Projection of x1, projection of y1, projection of z1 on x0, y0, z0. Everyone with me? Now x1, can you see that x1 is aligned with x0? Do you agree with me? Y1 is aligned with z0. Z1 is aligned with. So can you see that Z1 is coming outside, out of the board. Y0 is going inside the board, which means projection of Z1 on Y0 will be -1. Everyone understood this? Zero, -1, 0. Now what you need to do is, you need to multiply first row, first column, first row, second column, first row, third column, first row, third column, minus, minus plus, sine theta 1. Then second row, first column, sine theta 1. Second row, second column, 0. Second row, third column, minus cosine theta 1. Third row, first column, third row, second column, third row, third column. Just to be clear, this is sine. Okay. Now, once this is done, set up the homogeneous transformation 0h1. In 0h1, you get cosine theta 1, 0, sine theta 1, sine theta 1, 0, minus cosine theta 1, 0, 1, 0, 0, 0, 0, 1. And here, distance from frame 1 to frame 0 along x0, along y0, along z0. So can you see the distance from frame 1, which is frame 1? This is the frame 1. This is the frame 0. This is the frame 1. Can you see that x0, 0, 0, and this is A1? Do you agree with me? Now comes the tricky part. Now tricky part is, I need to note frame 2, frame 2 and frame 1 do not satisfy rule. So whenever you have a case like this, what we do is we translate frame 2 onto frame 1. Whenever the rules are not satisfied, for the purpose of analysis, we are going to translate frame 2 onto frame 1, which means this frame, which was here, and I'm going to draw this one more time here so that everyone understands. This is my frame 2. So this is frame 1. This is frame 1. This is Z1. Then I have Y1. And then I have X1. And then what I have is I have this frame, which is X2, Y2, and Z2. X2, Y2, Z2. These two frames, clearly X2 is perpendicular to Z2. x2 is perpendicular to z1, but x2 is not intersecting z1. Anyone understood this? So what I'm going to do is I'm going to take this frame physically from this location and move it onto this location. So this frame, what I'm going to do is I'm going to move this frame onto this location. So now the new frame, so this is frame translation, frame 2 translated here, Z2 and Y2. You agree with me? So now I have frame 2 was not satisfying the rule. As soon as I translated the frame, you agree with me, all the rules are satisfied. Now I would set up one R2. I would set up one R2. One R2 is going to be cosine theta 2 minus sine theta 2, sine theta 2, cosine theta 2, 0, 0, 0, 0, 1. Multiplied by the projection matrix. Now the new frame is x2, y2, z2, x1, y1, z1. Now since we have translated the frame, check this out. You should not be looking at frame, you should be looking at this frame, the translated frame. Now observe x2 is aligned with y1, y2 is aligned with z1, and z2 is aligned with x1. So when you perform these calculations, first row first column is going to give you 0. First row first column is going to give you minus sine theta 2. First row second column is going to give you 0. First row third column is going to give you cosine theta 2. Second row first column is going to give you cosine theta 2. Second row second column is going to give you 0. Second row third column is going to give you sine theta 2. Third row first column is going to give you 0. Third row second column is going to give you 1. And then you are going to get this. Are you with me? Now we need to set up the homogeneous transformation matrix. So 1H2. In homogeneous transformation matrix, you actually rewrite 1R2 as is. So 1R2 would be written as minus sine theta 2, 0, cosine theta 2, cosine theta 2, 0, sine theta 2, 0, 1, 0, 0, 0, 0. And then you are going to have last column, last row, fourth column as 1. Now here comes a tricky question. This is the distance between frame 3, this is frame 2 and frame 1. Frame 2 and frame 1 along x1. Distance between frame 2 and frame 1 along y1. Distance between frame 2 and frame 1 along z1. Now my question to you is, what should I write here? What should I write here and what should I write here? Remember, we have translated the frame. We have translated the frame, which means right now these two frames are on top of each other, which means there is no relative distance, which means it's gonna be 0, 0, and 0. You agree with me? Why did we translate the frame? We translate the frame because the rules were not getting satisfied. Now, after translation, the rules got satisfied, and because of that, there is no distance, there is no offset between these two frames. Now we continue to the next frame. Now, next frame is the last frame, which is over here. So the last frame is over here. So this is Z3. This is Y3, X3. Z3, Y3, X3. This is where your end effector is. Now, let me ask you a very important question. What is going to be my 2R3? What is going to be my 2R3? Now, please understand, it's a prismatic joint. It does not have any rotational degree of freedom, which means for the prismatic joint, the rotation matrix is going to be identity. So for prismatic joint, the rotational matrix is going to be identity 1, 0, 0, 0, 1, 0, 0, 0, 1. Now, can someone tell me about the projection matrix? Whenever you find the projection matrix, look at frame number 3. I mean, frame number, frame number 3, the X3, Y3, Z3, which is frame number 2. And compare that with the previous frame. Since everything is aligned, so I need to write this down. So X3, Y3, Z3, X2, Y2, Z2. Can you see this is again an identity matrix? So all said and done, what you have is an identity matrix. Can you see that this Z3 is aligned with this Z2? This X3 is aligned with this X2. And this Y3 is aligned with this Y2. So everything is aligned. So the homogeneous transformation matrix, and now this is the tricky part, 2H3. The first rotation matrix will be 1, 0, 0, 0, 1, 0, 0, 0, 1. Oh. And then what I need to have is I need to have the fourth row 0, 0, 0. I'm going to have 1 here. And now what I need is the distance between this end effector frame, distance between this end effector frame, F0, F1, F2, and F3. This is F3. So this is between F3 and F2 along X2, F3 and F2 along Y2, F3 and F2 along Z2. Now look at this figure. This distance is A2. This distance is A2. This distance is A3. Now, please note, this F2 should be the translated frame, okay? This is the translated. So this is the translated frame. So can someone tell me what is the distance between the translated frame 2 and frame 3 along X2? Yeah. We need to add A2 and A3. But the question here is, once again, remember, you have to consider the frame that is translated. So the translated frame, and I need to write this down just to make it clear. Let me see. The frame here, this is the frame that you should be focusing now. This frame is Z2, Y2, X2. Can you see that frame X2 means the distance between the frame 2 and frame 3 along X2 is 0. Distance between frame 2 and frame 3 along Y2 is also 0. But the distance between frame 3 and frame 2, remember the translated frame 2, along Z2 is A2 plus A3. It is just A2 plus A3, not A2 plus A3 cosine theta, not A2 plus A3 sine theta, or anything like that. You agree with me? You have understood this? So the only change here is going to be 0, 0, A2 plus A3. Everyone understood this? Now, your forward kinematics problem, if you want to solve, you have to find 0H3, which is 0H1, 1H2, 2H3, and you will get a final matrix. And what are your inputs? Your joint angles or joint values are theta 1, theta 2, and D3. So these are your inputs, and your outputs are gonna be end effector position X, end effector position Y, and end effector position Z. Everyone understood this? Question? Yeah.
So when we talk about distance between frame 2 and frame 3,
Right.
The condition A2 plus A3, that would only work if we are talking about distance between J2 and J2, because we are translating F2, F3 to F. We are translating F2 onto F1, right? So the distance between the frames will become 0.
Distance between
The
frame 2 and frame
1 will become 0.
So this is the frame 1. This is frame 1. This is frame 1. Frame 1. This is frame 2. And this is frame 3. Now frame 2 and frame 1 do not satisfy the condition. So we translated frame 2 from its original location to frame 1 for analysis purpose. We found out the homogeneous matrix when frame 2 was translated. Now, when we are trying to find out the relationship between frame 2 and frame 3, remember our frame 2 is here and our frame 3 is all the way over here. which means the distance between frame 2 and frame 3 exists along Z2, which is A2 plus A3. It is just A2 plus A3. It is not A2 plus A3 cosine theta 2. It's not A2 plus A3 sine theta 2. Because our frame, which is frame 2, has been translated at the location of frame 1. You understood this? Remember this is a very important aspect when you solve forward kinematics. Now the next part is, I have emailed you a couple of MATLAB codes for this particular problem. Just use the MATLAB code, solve the forward kinematics problem, use the MATLAB solve function, and find the solution of the inverse kinematics problem. And I would explain that code line by line, but I want to talk about one more important case. Yeah. Yeah, so basically you're right. So what I need to do is, you're absolutely right. I made a mistake here. I would just add A3 plus D3 plus D3 because A2 and A3 are constant. So I forgot to add D3 here. The distance between frame 2 and frame 3 is A2 plus A3 plus D3. Everyone understood this? Now there is another case that I want to discuss. Now imagine, and this is a very important case. And why this case is important? Because if you take robotics 2 class, we are going to talk about unmanned aerial vehicles, whether it's a fixed wing, whether it's a quadcopter, whether it's a vertical takeoff and landing, whether it's a rocket, whether it's a missile, whether it's a stone flying through the air, you can treat that as a spherical risk. The next question, that next problem that I want to solve is the problem, which is a very, very important problem in kinematics, which is called as the spherical risk. What is spherical risk? Spherical risk is you have 3 revolute joints. These 3 revolute joints are perpendicular to each other. You have R, perpendicular to R, perpendicular to R. And spherical risk problem is very important because you encounter something called as the gimbal lock. Okay, now what I want to do is, let me set up the problem, explain what is gimbal lock, and then we will solve the forward kinematics for the spherical wrist. In spherical wrist, you have the first revolute joint, then you have the second revolute joint, and you have this third revolute joint. You have this third revolute joint. You have this first revolute joint. You have this second revolute joint. You have this third revolute joint. Do you agree with me? This is the spherical wrist. Now, this joint is called as yaw. This joint is called as yaw. This joint is called as pitch. And this joint is called as roll. And I want you, this nomenclature is very consistent with a helicopter, fixed wing, quadcopter convention. So what you have is, this is your x. This is your x. This is your y. And this is your z. This is called as north, east, down coordinate frame. North, east, and down coordinate frame. So rotation about z-axis is yaw. Rotation about y-axis is pitch, and rotation about x-axis is rho. So you have yaw, pitch, and rho. You agree with me? Now I want you for a minute to visualize a very special configuration. I want you to visualize a very special configuration in your mind. At this point, your pitch angle is 0. You agree with me? Your pitch angle is 0. Imagine that pitch angle increases, and it becomes 90 degrees. When the pitch angle becomes 90 degrees, what happens is you have the first revolute joint, you have the second revolute joint, and the third revolute joint, and I want you to notice this is very important observation. You have this third revolute joint, which is something like this. So you have the first, let me draw this properly. So what you have is you have this first revolute joint, then you have the second revolute joint, and then the second revolute joint has this third revolute joint, which is like this. So there is your revolute joint, this is your revolute joint, this is your revolute joint. Do you agree with me? Now, one important thing to observe, that the axis of the third revolute joint, coincides with the axis of the first revolute joint. So at 90-degree pitch, axis of third revolute joint aligns with axis of first revolute joint. Everyone understood this? Can you visualize that if I rotate the joint number 2, looking at the configuration that we have, the third revolute joint aligns with the first revolute joint. Now here is the problem. Whenever something like this happens, there are actually 3 revolute joints. So you have theta 1, theta 2, theta 3. So check this out. You have yaw, you have pitch, and you have roll. Yaw is about the z-axis, pitch is about the y-axis, and roll is about the x-axis. At 90-degree pitch, yaw and roll, they are aligned. It means you cannot distinguish yaw from roll. To give you an example, I want you to notice in this particular case, I give 30-degree yaw, and I give 30-degree roll. Do you agree with me that both these rotations are going to result in some unique configuration? You agree with me? And when you work out the math, I'll show it to you. So I want you to understand 30-degree yaw If I give 30-degree yaw, my role is not changing. You agree with me? In other words, if I give you 30-degree yaw and I give you minus 30-degree roll, your effect is not cancelling. You agree with me? Yaw remains yaw, roll remains roll. Now in gimbal law, observe, if I do 30-degree yaw plus and then I do 30-degree roll minus, I get back the same position. Once again, in this particular configuration, when pitch is anything else than 90 degrees, yaw and roll, they are independent. Rotation in yaw and rotation in the roll, they are independent of each other. Yaw does not affect roll. In other words, yaw cannot cancel roll or roll cannot cancel yaw. But when the pitch is 90 degrees, positive yaw and negative pitch, if they have the same magnitude, they cancel out each other. Which means effectively you lost control over 1 degree of freedom. You agree with me? That is called as the gimbal lock. And this gimbal lock is a major issue. That's why whenever you are trying to solve the computer graphics problem, when you are trying to solve the robotics problem, whenever you are trying to solve the aircraft kinematics problem, you don't use Euler angles. Yaw, pitch, and roll. G, Y, X. This is a very common Euler angle configuration that is used to describe orientation. But the fundamental limitation of Euler angle is Euler angles suffer from gimbal law. At 90-degree pitch, you cannot solve yaw and pitch, yaw and roll independently. Everyone understood this? Now I'm going to set up a forward kinematics problem for this, and then we'll work out the MATLAB code. So again, step number 1, add this as Z0. This I'm going to call as X0. This is going to be Z1. Then again, this is going to be Z2. And this is going to be Z3. So you have X2, so a Z0. Now my question to you is, where should my X1 be? Where should my X1 be? My X1, I'm gonna have my X1 over here. Now the question is, where should my X2 be? And you see that I have two options for X2. I can draw my X2 like this, or I can draw my X2 maybe something like this. But no matter where I draw my X2, my rules are not satisfied. Can you notice that? If I draw X2 perpendicular in the vertical direction to Z2, or if I draw X2 coming out of the board, my X2 is not going to intersect Z1. So if I want my X2, to be perpendicular to Z1, and if I want my X2 to be intersecting to Z1, my best possible choice is this X2. And then I'm going to call this my X3, and then I will complete the triad. X, X, Z is going to be my Y. This is going to be my Y naught. I have X, then I have Z, X, Z, then I will have, yeah, X1 should be perpendicular, right? I made a mistake here. X1 should be like this. X1 should be like this. Then this is my X1, Z1, this is gonna be my Y1. Then I have Z, X, this is going to be my Y2. And this is going to be my Y3. Okay, I will give a minute for you to check that my X1 is perpendicular to Z1, X1 is intersecting Z0. X1 and Z0, they are 90 degrees. Now, in the case of X2, no matter what configuration I use, my X2 cannot intersect with Z1. But at least in this particular case, if I were to translate the frame, frame number 2 to frame number 1 location, my X2 and my Z1 will be perpendicular. So what I'm going to do now is I'm going to assign the distances, and these distances are A1, this distance is going to be A2, and this distance is going to be A3. You have A1, you have A2, and you have A3. Any questions about the coordinate system? Now what I would do is, I would do 0 R1. This is my theta 1. This is my theta 2. And this is going to be my theta 3. 0 R1 is cosine theta 1 minus sine theta 1, sine theta 1, cosine theta 1, 0, 0, 0, 0, 1. Let's not forget the projection matrix. X1, Y1, Z1, X0, Y0, Z0. So check this out. X1. So X1 is aligned with X0. Y1 is aligned with Z0. And Z1 is aligned with minus Y0. So you get, when you multiply these terms all together, you get cosine theta 1, first row, first column, then 0, first row cosine theta 1, sine theta 1, first row, second column 0, first row, third column minus cosine theta 1, 0, 1, 0. Now the homogeneous transformation matrix, 0, H1, it's gonna be cosine theta 1, 0, sine theta 1, sine theta 1, 0, minus cosine theta 1, 0, 1, 0, 0, 0, 0. You have 1 over here. And then since this distance is A1, it's going to be 0, 0, A1. This is going to be the first homogeneous transformation. Next, now I need to find out 1 R2. Now problem with 1 R2 is note that this frame does not satisfy the rule. This frame does not satisfy the rule. So what I'm going to do is I'm going to translate that frame. I'm going to translate that frame 2 onto frame 1. As soon as I translate that frame, this frame on here, now I need to look at this frame, which is x2, z2, and y2. So I have x2, z2, and y2. Now, please pay attention. Again, there is a revolute joint here. So this is going to be cosine theta 2 minus sine theta 2, 0, sine theta 2, cosine theta 2, 0, 0, 0, 1. Now this is going to be x2, y2, z2, x1, y1, z1. What I want you to do is, I want you to look at the gray frame and the black frame. X2 is aligned with y1. X2 is aligned with y1. 0, y1 here, 0. y2 is aligned with z1. And z2 is aligned with x1. So when you multiply this, you are going to get cosine theta. So you are going to get sine theta 2. First row, first column. First row, second column. First row, third column, cosine theta 2. Second row, first column, cosine theta 2. Second row, second column, 0. Second row, third column, sine theta 2. First row, third row, first column. Third row, second column. Third row, third column, 0. Now to find 0, so 1 H2, I have minus sine theta 2, 0 cosine theta 2, cosine theta 2, 0 sine theta 2, 0, 1, 0. Now 0, 0, 0, and I have 1 over here. Now I want you to answer this question. What is the relative distance between the translated frame 2 and the original frame 1? What is the distance between the translated frame 2? You see that we translated the frame 2 on top of frame 1 so that the rules can be satisfied. Now these two frames are on top of each other, which means there is no relative distance. So x is 0, y is 0, z is 0. Do you agree with me? Now next, I need to look at the last rotation, which is 2R3. 2R3 rotation, same thing, x3, y3, z3. This is the projection off, projection on. Cosine theta 3 minus sine theta 3, sine theta 3, cosine theta 3, 0, 0, 0, 0, 1. Now look, x3 is aligned with x2. Are you with me? x3 is aligned with x2. Y3 is aligned with Y2. Z3 is aligned with Z2. So this matrix is an identity matrix. So this matrix is going to be cosine theta 3 minus sine theta 3, 0, sine theta 2, cosine theta 2, 0, 0, 0, 1. The last but not least is 2H3. 2H3 is cosine theta 3 minus sine theta 3, 0, sine theta 3, cosine theta 3, 0, 0, 0, 1. And then you have, this is the tricky question. Now tell me, what should I write for the distances between the frame 3, which is, this is frame 3, and translated frame 2? Tell me, what should I write there? No cosine theta, no sine theta, no cosine theta 3, cosine theta 4. So your answer is correct. This would just be 0, 0, and A2 plus A3. A2 plus A3. And I want you to pay attention why there is no cosine theta 3, why there is no sine theta 3. Because try to understand, no matter what the rotation, the distance, the horizontal distance does not change. The axis is your Z2, and you are finding out the distance between the translated frame 2 and frame 3. The distance between x is 0. Distance y distance is 0. Z distance is A2 and A3. No matter how much you rotate your joint theta 3, that distance is not going to change. That's it. Now we have found out the forward kinematics. So 0H3 is 0H1, 1H2, and 2H3. And in next class, I would show you how to solve. I will walk you through the code for forward kinematics, inverse kinematics for these two cases where the rules are not satisfied, and then we will start with the velocity analysis. But before that, I want to talk about the project. By the way, first midterm project is coming, and that's not easy. You remember what you have to do? So midterm 1, so midterm is build a tic tac toe. Now there are two ways to build this. One is a very easy way, and one is a difficult way. If you want to solve this problem with easy way, you can just use Google and find tic-tac-toe play robot using robot addition. You will get a GitHub repo. You can use that repo and build a tic-tac-toe play robot. And maybe that will give you the grade, but that will not give you the job. Now I'm gonna tell you how I would like you to implement this. And trust me this. Do this the way I tell you to do it. Create a very nice video, upload that on LinkedIn, and I promise you that you will get call from recruiters. That's my promise. Here is, and it's all recorded. Okay. So here is what I want you to do this. I want you to use agentic AI. What is an agentic AI? If you don't know what is agentic AI is writing the code using LLMs. So what you do is you create agents, and there are frameworks. So just Google agentic AI, no code agentic AI frameworks. You can build an agentic AI framework without actually writing any code. You would use ChatGPT or Gemini to write the code. Couple of ones that I have used is there is a tool by Microsoft for agentic AI. There is a tool which is called as Promptly, which also integrates RAG. So those are fantastic tools. So here is how you should build a tic-tac-toe playing robot. What you should have, agentic AI uses LLM or VLMs to solve the problem. So you have LLMs in the back. You use an agentic AI framework, and if you give me 2 minutes and I'll show you which agentic AI frameworks you can use. What you would do is you will create one agent. This agent will actually take the so this agent will basically draw the grid. So this agent, what will this will do is only draw grid. Second agent will take the snapshot of the grid. So you draw the grid, the operator draws X or circles it. The second agent will take a snapshot of that grid. Every agent has something called as skills. Skills are nothing but the Python functions that are written by the LLMs. So that Python function that you generate, you can use OpenCV. That Python function should identify whether it's an X or whether it's an O and where it is drawn. So your grid should be 1 1 1 2 1 3, 2 1 2 2 2 3, 3 1 3 2 3 3. So you have a 3 by 3 matrix. The second agent should take a snapshot and identify the location in the matrix where X or O is drawn. You agree with me? So this would be the second agent that would detect X or O and their location. And there are only 9 locations possible. Okay. If it recognizes multiple X's, multiple O's, then clearly that agent should throw an error. The first iteration, that agent should only detect one X or O. Once this agent detects O, and you'll actually write a Python skill using LLM. LLM will write the code. When LLM writes the code, you should upload the snippet of the code that you wrote for the object detection. Only then LLM will give you a code that will actually work. If you ask LLM to generate the code, it will give you a random code that will not work. But you have to provide the snippet to the LLM and say that convert this code to detect X and O's. It will do it very nicely. The second agent should identify X and O. Then you should have the third agent. You should have the third agent. This third agent should give you the possible or the best possible location for X or O in the matrix. Everyone understood this? And then you should have a supervisory AI or supervisory agent. This agent should detect whether you have 3 X's or 3 O's in line. If that is not the case, then it needs to check if out of those 9, how many blocks or how many entries are completed. And based on that, this agent should pass it back to the second agent. Second agent should pass it back to the third agent. And this process continues till you have 8 of the 8 of the 9 points filled, or at least you get you are able to draw the line. The same tic-tac-toe algorithm that if you go online, then you will find a tic-tac-toe algorithm using MATLAB, tic-tac-toe algorithm using Python, tic-tac-toe algorithm using OpenCV. But this type of framework, right now, agentic AI is super duper hard. If you go to Silicon Valley, they are looking for engineers, they are familiar with agentic AI. Agentic AI is expected to revolutionize the world of artificial intelligence. There are free 1.5 hour courses on LinkedIn Learning on agentic AI. It's very simple. So I want you, if you are looking for an internship, or if you are looking for a high-paying job. Oh, by the way, my student day before yesterday got 2 offers. One from Google, one from Meta. I don't even ask salary. He's going to earn more than me. Why are you saying? Because I want my students to be more successful. Hopefully, some of you will become multimillionaires. Okay. Then build this agentic AI. Create a very nice video. Add this agentic AI. Showcase this agentic AI project in your portfolio. And I promise you, will get received calls. Okay. That being said, I want to kind of share with you a couple of agentic AI frameworks. How many of you know about agentic AI? If you don't know, high time you should start knowing about it. So you should go to agentic AI framework. So agentic AI frameworks. So Microsoft AutoGen is a very, very straightforward agentic AI framework. Then I have used something called as Promptly. So Promptly. So you can actually use that Promptly agentic AI framework. The beauty of that is you can actually input your robot APIs, and it will actually use the RAG to give you a very nice code. So this is my challenge to you. Let me see how many of you build this tic-tac-toe playing robot using agentic AI. Agentic AI is the next big thing in AI. If you don't believe me, next month go visit San Francisco. There is TechCrunch Disrupts and see what they are talking about. Okay, with that, I'm going to stop here. I would be happy to answer any questions after the class. TechCrunch. TechCrunch Disrupt.